In this section, we're going to look again at the dimension of a vector space. Again, we've already been introduced to the idea of a dimension. We're going to look at it in a little bit more detail here. Start out with Theorem 10. So we start out with a basis for a vector space. Then this theorem says that if we have any set with more vectors than that in it, it has to be linearly dependent. Okay, so here we're seeing some more of the connections between all of the concepts we've seen. The idea of a basis, which is linearly independent, sitting inside of a vector space, and that in essence, that means that this is the largest size you can ever get without it being linearly dependent. So it doesn't matter if you take your basis and add something to it, or you have a basis that has n vectors. If you take any set of vectors out of there where you have more than n vectors, it's automatically linearly dependent. So this is essentially a maximum limit on the size of a set to be linearly independent. And why is this? Well, let's just say that we have a set of vectors, any set of vectors that's bigger than the basis. So we have a basis with n elements, and we have any other set of vectors with more than that. Well, we're going to reach back to our coordinate system to show this. Well, all of these vectors, because we have the basis, we can get the coordinates of every one of these vectors in that basis. So we can get the coordinates of our first one and all the way up to the coordinates of our pth one. So this is giving us p vectors. Each vector are the coordinates of that vector in that basis. So each vector has n elements in it. So stick them all together. What do we have? We have p vectors with n elements, but because p is bigger than n, that means that we have more vectors than elements in each vector. So it's like having 4 elements in R3. Right away, it's linearly dependent. We already know that. Okay. So this set of coordinates are linearly dependent. Now that's not the vectors we started with. These are the coordinates. We now know the coordinates are linearly dependent. But if they're linearly dependent, by definition, it means that we have non-trivial scalars that we can add things up and get a 0. So we have these c's where something in there, some of those c's are non-zero, and they add up to 0. But now here we're going to use a fact that we kind of talked about last time. This transformation, this coordinates by a basis is a linear transformation. So this C1 times the coordinates is a linear transformation from R2, Rn into Rn. So since this is a linear transformation, we can combine them to get that. Basically, the linear transformation means that scalar multiplication and vector addition is preserved. So instead of taking each vector and doing the transformation on it, we can combine all the vectors first and then do the transformation. We get the same exact thing. And that's equal to 0. So this step is using the properties of a linear transformation and knowing that this function is a linear transformation. So since any linear transformation, one of the properties of a linear transformation is that it transforms the 0 vector into the 0 vector. So we get that 0 is equal to that. You also have to use the fact that it's onto here. So it's an isomorphism, so it's an onto. It's 1-to-1. So we get that since our transformation x into xb is 1-to-1. Okay, so we have to use that fact. But we start off by saying this is a non-trivial solution. Not all the coefficients of 0 are 0, so that set itself has to be linearly dependent. So this is a neat little trick that we did here to prove it. And it's using some of the things we saw last time. It uses the idea of coordinate bases, and it uses the fact that these coordinate bases are a linear transformation, and then uses some properties of linear transformation. This proof, as I said, pulls together some of the earlier ideas, and if you can get your head around this proof, it's a really good way of understanding, of knowing that you understand the topics we've done so far. But now this leads to theorem 11. So we talked about having a basis of n elements. So a vector space has a basis, and there are n elements in it. Theorem 7 says that every basis has exactly n elements. So we've talked about how there are all kinds of bases for a vector space. No, a basis isn't unique. There are all kinds of them. What this says is that they are kind of unique in that they are all the exact same size. Now, this is an idea that we have seen before, but here's the proof of it. So suppose that you have a basis with n elements and a second basis with p elements, and they're both bases of this vector space. From the theorem we just saw that if p is bigger than n, then that means the elements of our second basis, if there's more elements in there, they're automatically linearly dependent. What does that mean? That means it's not a basis, because a basis, the elements of a basis have to be linearly independent. So right away, if the second basis is bigger, then that means it's linearly dependent, so it can't happen. So it has to be no bigger than the first one. But then turn it around, likewise, if the first one has more elements, then that's linearly dependent, because B2 is a basis. So that means neither one can be bigger than the other one. So the two sets have to be the same size. So this is telling us that for any vector space, there are infinitely many bases for a vector space, for the vector spaces we're dealing with. Any of those bases have the exact same number of elements. And that number is called the dimension of V. So if you have a finite set that spans it, it's called a finite dimensional vector space, and the number of vectors in there are the vectors that span it. It is also possible that you can have a vector space that is infinite dimensional. Okay, so there is an example of that if you take the set of all polynomials, what's a basis for that? A basis for the set of all polynomials is 1, x, x squared, x cubed, x fourth, x to the fifth, and so on. That is a basis for it, and it's infinitely dimensional. There is no finite basis for the set of all polynomials of all degrees. Okay? But it is a vector space. It is an infinitely dimensional vector space. We aren't focusing on infinite dimensional vector spaces, so that's a bit of an aside. We are working with finite dimensional vector spaces. And when you have a finite dimensional vector space, the size of a basis is called the dimension of the vector space. So theorem 12. This is when we have one vector space inside of another one. So we've seen lots of examples of this. So for instance, we have R4 with all the vectors A, B, C, 0. That's a vector space inside of R4. So this deals with subspaces, vector spaces that are inside another one. So if we have H that's inside of V, and H is a vector space and V is a vector space, and you take any linearly independent set in H, this theorem says you can grow that just by adding some more vectors in to become a basis. And that basis for H that you end up with is less than or equal to the dimension of V. So this kind of makes sense. If you have a vector space that's inside another vector space, it means that its basis is going to be no bigger than the basis of the bigger one. The dimension is going to be smaller or equal to. So why is that? Well, first off, when we do the proof of it, first off we deal with the easy one. If our subspace is the zero subspace, then the dimension is 0, and it's always going to be less than or equal to the dimension of the bigger one. Okay? So we get that one out of the way. So now we say that our space has at least one vector in it other than the 0 vector. So it has some other vector in it. So take any linearly independent set in there. It may not be a basis, it's just a linearly independent set. Because remember, a basis also has to span. So in other words, this doesn't span everything. If it's not a basis, but it's linearly independent, then that means it doesn't span. So if it doesn't span H, then there's something in H that is not in that span. Pick one thing in it, in H, that's not in the span, and stick it in there. So we find some vector in H that is not in the span that we started with, and we just add it. Well, because it wasn't in the span before, adding it in means that this set that we have, the bigger set, is still linearly independent because you can't build it from what was already there. But now it's a bigger set that's linearly independent. And you just keep doing this over and over and over again. So if the set that you end up with doesn't yet span H, add in another vector that's not in the span, and keep doing it until you can't do that anymore. At some point, you're going to run out of vectors that you can add in. But our previous theorem said that it can never get any bigger than the dimension of V. Because H is sitting inside V, if it gets bigger than the dimension of V, then it's linearly dependent. So the span or the dimension of H can never be any more than the dimension of V. Next theorem, theorem 13. When we're dealing with a vector space, a p-dimensional vector space, a couple of things. If you know the dimension and you have any linearly independent set of that with that many elements in it, it's automatically a basis. And any set of p elements that spans V is automatically a basis. So we talked about how a basis is a set of vectors that are linearly independent and span the vector space. What this says is that if we know the dimension, then if you want to confirm that, you don't have to check both conditions. You just have to check one of them. If you have the same number of vectors as the dimension, you don't have to check both conditions for a basis. You only have to check one of them, and the other one is automatically satisfied. So why is this? Well, let's say we have a linearly independent set of p elements. From the theorem we just saw, we saw how if it doesn't span it, you can just keep adding more elements in. You can add more elements in. But we know that a basis has to have exactly that many elements, exactly p elements. So you can't do that. As soon as you add something else in, it becomes linearly dependent. So it's as big as it can get, it has to span it. So there can't be anything in there that it doesn't span. If there were something, you could add it in and you could get a bigger set of linearly independent vectors, but you can't do that. So it has to be the span, therefore it has to be the basis. Now, what if you know that you have the span? What if you, for the second part, what if you know that you have a set of p elements that spans it? Well, the spanning set theorem that we saw a little while back implies that there has to be some subset of it that's a basis. So if you have a set that spans it, then you can pick out some vectors in it that span it. But since you already have the right number in there, then that smaller set has to have exactly that number, so there's nothing you can take out. If you take anything out, you become smaller than your basis, which you're not allowed to do. So that smaller set has to be the same as your bigger set. So this is using another idea that you'll see quite often in mathematical theorems. It says that if you have a set that you want to show does something, well, take a smaller set, a subset of it, and show that if that smaller subset does it, it has to be the same as the bigger set. So this is a bit of a mathematical idea that you use quite often in proofs. So now a definition. The rank of a matrix. The rank of a matrix is the dimension of its column space. So remember, we've dealt with the column space quite a bit. The rank is the dimension of the column space. It's also equal to the dimension of the row space. Because remember, the row space is just the column space of the transposed matrix. So the dimension of the row space is equal to the dimension of the column space. So that's the rank. The nullity of a matrix is the dimension of the null space. So we've dealt with the null space a lot, and I think we've already seen this idea about the rank and the nullity. And this leads to one of the cornerstone theorems of linear algebra. If you have an m by n matrix, the rank plus the nullity is equal to n, where n, remember, that's the number of columns. So the rank of a matrix plus the nullity of a matrix is equal to the number of columns. And what's the proof of that? Well, just a sketch of the proof. Think about how you get the number of elements in a basis for the column space and how you get the basis for the null space. You row reduce. To get the column space, you pick the columns that are pivot columns. To get the null space, you have these free variables. How many free variables are there? It's the non-pivot columns. So a pivot column, the number of pivot columns is the rank. The number of non-pivot columns is the nullity. You add them up, you get the number of columns. So this theorem is using the ideas that we've seen, the techniques that we've seen, but it is a fundamental theorem of linear algebra, that the rank plus the nullity is equal to the number of columns. So as just an example of using this. If we have a 7 by 9 matrix with a two-dimensional null space, what's the rank of A? Well, 7 by 9, the number of columns is equal to 9. So the rank of A is equal to 9 minus the nullity of A. We saw that the nullity is 2, so it's 9 minus 2, which is equal to 7. The rank of it is 7. The second one, if we have a 6 by 9 matrix, well, can it have a two-dimensional null space? Well, the answer to this is no. We only have 6 rows, so there can only be 6 pivot columns. There can only be 6 pivot entries. So there can be, at most, 6 pivot entries. So the rank of A has to be less than or equal to 6. But the rank of A plus the nullity of A has to equal 9. So the rank of A has to be greater than or equal to 7. So it cannot be 6. So rank of A sorry. So the rank of A has to be greater than or equal to 7 if the nullity of A is equal to 2. That's a contradiction. It can't happen. All right. This was a fairly short section for me to talk through. It is mainly focused around some theorems and some of the proofs around some of these ideas of linear algebra that is pulling together a lot of the ideas that we have seen so far. It is, if it takes you a little bit to get your head around it, that's fine. But these are some of the critical theorems and critical ideas in linear algebra. So it's worth spending a little bit of time on this section to try to understand these theorems, work through some of the problems in the book to try to clarify some of the ideas.